Hello everyone, this is Dr. Fan. Consider you are walking on the road. What's the friction between you and the road? Consider the ball rolling down a ramp. What's the friction between the ball and the ramp? Also consider a moving car. What's the friction between a tire and the road? The answer is, although for three scenarios, everything is moving, but it's all static friction. And the friction force does not equals to mu s times the normal force. In order to understand all this, we got to understand the key concept about friction, and we're gonna do it today. Alright, let's first check the definition of friction, then we're gonna do some practice problem. So friction is a force that opposes relative motion between contacting surface, and the friction force is always parallel to the contact surface. So if I'm pulling this box to the right, and the contact surface between the box and the table is right here, so there is a resisting force opposing this motion. If the box is actually moving to the right, then you're going to have kinetic friction. So if the two surfaces are in contact and moving relative to each other, the friction is kinetic friction. But if I'm pulling this box and the box only has a potential movement to the right, it doesn't actually move, then there is static friction. So static friction could occur if there is a potential relative motion. And usually static friction is larger than kinetic friction. So this is the definition of friction. And if you want to do the calculation, we know that the kinetic friction, it equals to the kinetic friction coefficient times the normal force. So if you have kinetic friction, the friction force is a fixed value. But for static friction, it's not a fixed value. Instead, it's a range. So the maximum value for static friction equals to mu s, the static friction coefficient, times the normal force. So remember, static friction is a range. It's smaller or equals to mu s times the normal force. Alright, that's enough for the concept, and let's work on some practice problems. Alright, let's see there is a box, and the box weighs 100 Newton, and the static friction coefficient between the box and the platform is 0.2, and the kinetic friction coefficient is 0.15. How should we apply a horizontal force so that the box can move without acceleration? So when we look at this question, the first thing we can do is do a free body diagram. So we know the box is under gravity, so we just write this down, gravity, and we know there is a supporting force from the platform. If we apply a force to the right, there may be a friction force opposing this relative motion to the left, right? So these are the possible forces here. If we look at the net external force along y direction, Fn minus Fg, we know it equals to 0 because there is no vertical motion. So we know the gravity equals to 100 Newton, and the gravity and the normal force are the same, so the normal force is also 100 Newton. And now let's look at the horizontal direction. So along the horizontal direction, there is this applied force, and the friction force is going to the opposite direction. And based on Newton's second law, it equals to mass times acceleration. So if we want to make sure it moves without acceleration, in other words, we want to have constant velocity, so the acceleration should be 0. So how should we apply this force? So before we talk about how should we apply this force, let's first calculate the kinetic friction force and the static friction force. We know for the kinetic friction force, it's very straightforward. It equals to mu k times the normal force. And in this case, the mu k is 0.15, so it equals to 0.15 times 100 Newton, so it equals to 15 Newton. And we know the static friction force is a range. It's smaller or equals to mu s times the normal force. And the static friction coefficient is 0.2, so it equals to 0.2 times 100 Newton, and which equals to 20 Newton. So that means the maximum static friction force is 20, but the kinetic friction force is 15. Now let's think about how we should apply this force so the box can move without acceleration. Let me draw this chart here. So let's see, this is the force, this is the time. And in the beginning, my force is 0. Then I gradually start to increase the force. Let me use a different color. So consider if I apply a force which is 1 Newton. Then this table, or you can call it a platform, this platform and the box has a contacting surface. And remember, friction force is along the contacting surface and opposing the motion, so the friction is parallel to the contacting surface to the left. So if I apply 1 Newton, then the friction force is going to be 1 Newton, which is coming from my static friction force, so that the box would not move at all. If I increase my force to 2 Newton, the static friction force can be 2 Newton opposing the motion, so the box would not move. And because we know the static friction force can be as large as 20 Newton, so that means as long as the force, applied force, is under 20, my box would not move. So let's assume I increase the force 1 Newton per second. So I do something like this. I do a linear increase. And after 20 seconds, my applied force is 20 Newton. And from 0 to 20 seconds, my force gradually increases to 20 Newton. What happens to the box? There is no motion. And the static friction force works during this regime. And what if my force is above 20 Newton? Then that exceeds the maximum static friction force. Then the box is going to move. So when the box actually moves, then kinetic friction kicks in. And the kinetic friction force is 15 Newton, is smaller than 20 Newton. So in order for the acceleration to be 0, I got to make sure my applied force is the same as my friction force. So that means once my force is slightly above 20 Newton, it's going to be kinetic friction. Then I should lower my force to 15 Newton. And I hold 15 Newton afterwards. In that case, my acceleration is 0. My box can move without any acceleration. In other words, constant velocity. And during this regime, I'm going to have kinetic friction. And the friction force is 15 Newton. So this example very well demonstrates what's the difference between the static friction force and the kinetic friction force. Alright, now let's look at another practice problem. So there are two plates at rest on a horizontal table, 1 and 2, and the mass of both plates are the same, which is 10 kg. And the static friction coefficient and the kinetic friction coefficient between the plates and the table are the same, 0.1. So if we apply a horizontal force on the lower block or on the lower plate, and we gradually increase the force, determine the motion of each plate when the force increases linearly from 0 to 50 Newton. Alright, this question can be quite long and complicated. Let's consider two special situations. Let's first consider the motion of two plates when a 10 Newton force is being applied. Alright, when we look at this situation, we got to do the free body diagram first. And if we look at block 1, let's do the free body diagram. So for block 1, there is gravity going down, and there's a normal force from 2 to 1. So I call this Fn1. Alright, So that's the force along vertical direction. I'm going to label the force along horizontal direction later. And for plate 2, this guy right here, this plate 2 also has gravity, which going down. So the platform is going to give it a supporting force, normal force. I call this Fn2. And there is another force along the vertical direction, which is the force from 1, which is the reaction force for this Fn1. So there is Fn1 going down. Why? Because number 2 plate is supporting number 1. As a reaction force, number 1 is pushing number 2 down. So these are the vertical forces, okay, for block 2. Now let's look at what we can learn from all these forces. For block 1, we know along the vertical direction it's not going to move. So that means Fn1 minus Fg equals to 0. So for block 2, along the vertical direction, we have the supporting force from the platform, which is Fn2, and minus Fg minus Fn1, which equals to 0, because there is no vertical motion. And we know both plates has the same mass. So the mass is 10 kg. So Fg1 equals to mg if we use 10 meters per second square, so which equals to 100 Newton. And the weight for the second plate are also 100 Newton, right? So what can we learn if we know the weight? From the weight, we can know the normal force right away, because Fn1 equals to Fg. So that means my normal force is 100 Newton. And for the second block, Fn2 minus 100 Newton minus the reaction force from this normal force, 100 Newton equals to 0. So the normal force from the platform to the plate 2 equals to 200 Newton. So once we know the normal force here, we can calculate the potential friction force. How do we calculate that? So for this question, the static friction coefficient and the kinetic friction coefficient are the same, are 0.1. So based on the normal force, based on the friction coefficient, we can find out the potential friction force. So between plate 1 and 2, because there's a normal force of 100 Newton, so the kinetic friction force equals to 0.1 times 100 Newton, so which is 10 Newton. And the static friction force between 1 and 2, the static friction force is smaller or equals to 0.1 times 100 Newton, so which is also 10 Newton. How about the friction force between plate 2 and the platform? We know its normal force is 200 Newton, so we're going to do the same calculation. So we know the kinetic friction force between the plate 2 and the platform is going to be 20 Newton. We also know that the static friction force is smaller or equals to 20 Newton. All right, so we know all this potential friction force. Now let's consider what happens if my applied force is 10 Newton. All right, so let me use a different color. So if the applied force is 10 Newton, right? Then block 2 or the plate 2 wants to move to the right. So the table give a resisting friction force, and the plate on the top may also give a force resisting this motion, right? And we know the maximum static friction force between the two plates are 10 Newton, and the maximum static friction force between 2 and the plate is 20 Newton. So how much friction force occurs between 1 and 2 and between 2 and the platform? Let's evaluate this situation. So if there is a friction force between 1 and 2, okay, so let's assume 1 apply a resisting force to 2. As a reaction, 2 is gonna provide a same amount of force to 1 in the opposite direction. And this is the only force on 1, so 1 is gonna move. And remember, friction always opposes the relative motion. In this case, 1 and 2, they actually gonna move with respect to each other, which is not what friction force wants to see. Instead, in this case, the friction force occurs only between 2 and the platform, which is exactly 10 Newton. And there is no friction force between 1 and 2. If this is the case, let's see what will happen if we write down the Newton's second law for block 2. So for block 2, let me use a different color. Along the horizontal direction, there is a 10 Newton applied force, and there is a friction force from the platform to block 2. 10 Newton go to the left. So the net external force for block 2 is 0. So number 2 plate is not going to move. And there is no friction between 1 and 2. So no friction in this case. So under 10 Newton, the motion is both of them are at rest. And the friction force from the plate to number 2 plate is static friction force, because there is no real motion. There is only a potential motion. So this is the motion if the applied force is 10 Newton. All right, let's now look at another situation. What if the applied force is 30 Newton? Okay, under this situation, things are different. So let's remember what we have already discussed. So between 1 and 2, the maximum static friction force is gonna be 10 Newton. And the kinetic friction force is also 10 Newton between 1 and 2. And we know between 2 and the platform, right? And we know the maximum static friction force is 20 Newton. And we know the kinetic friction force is also 20 Newton. Okay? So what will happen if the applied force is 30 Newton? So the applied force is 30 Newton. So some student may say the platform is going to oppose the motion. So there's a friction force from the platform to the plate. Let's write this as F platform to the plate 2. But we know this force can be as large as 20 Newton. So as large as 20 Newton. So if there is no friction force from 1, then plate 2 is going to move to the right. But plate 1 can actually resist this motion. So how much is the friction force between 1 and 2? Some students may say, okay, if I have a friction force from 1 to 2, let's call it friction force between the plate, let's call it friction force 1, right? So the student may say, oh, I can provide the force as large as 10 Newton. So how about I apply a 10 Newton friction force? So 10 plus 20 is 30, so it cancels out this 30 Newton, so everything's good. But the issue is, if the block 1 is giving a friction force on 2 to the left, as a reaction, 2 is going to give a same amount of force to 1 in the opposite direction. So this is FF1. In this case, the block 1 or the plate 1 actually moves to the right, which does not make sense. So how do we actually find out the friction force between 1 and 2? Newton's second law would help us. So let's do the free body diagram here. So for plate 1, if we consider the force on the horizontal direction, there is only one force. So this friction force, sigma Fx, equals to the mass of the upper plate times its acceleration. And if we look at block 2, so there is a force on the right, so this applied force minus the friction force from the table or the platform. Let's call it friction force from the platform. Then minus the friction force from 1. And if it's going to move, let's call it mass times acceleration. So the ideal case is this friction force is just right so that there's no relative motion between 1 and 2. That's the best situation. So this acceleration would be the same. So let's see if that's possible. Let's call this equation 1. This is my equation 2. So if I add equation 1 and equation 2 together, we're going to get this. F minus F friction force from the platform. These two values, they cancel out each other. On the right, you're basically only going to have 2m times a. Let's call this equation 3. So if we substitute the value in, so the applied force is 30 Newton, and because 2 is moving, so we should use kinetic friction force. So minus 20 Newton from the platform, which equals to 2 times the mass, which is 10 times acceleration. So after calculation, we know the acceleration is 0.5 meter per second square. And if I substitute this 0.5 meter per second square into equation 1, my friction force from 1 to 2 equals to 10 kg times the acceleration 0.5 meter per second square. This is 10 kg. So this is 5 Newton. So if I use a different color, so in reality, if block 1 can give block 2 a 5 Newton friction force, then both of them can move with the same acceleration, 0.5 meter per second square. In this case, between plate 2 and the platform, it's kinetic friction because they have real relative motion. But between 1 and 2, there is no real relative motion because they move together with the same acceleration. So this friction force is static, and this friction force is kinetic. Okay, so what would be our answer? Our answer is under 30 Newton force, block 1 and block 2, they move together with the same acceleration. And the friction between 2 and the platform is kinetic. Between 1 and 2, it's static. And the friction force is 5 Newton, which is smaller than the maximum allowed static friction force. Of course, you can also consider what happens if the applied force is 50 and 60. This is a very interesting question. I'm going to leave this to you guys. This is actually a real question in AP Physics C. So if you really understand this question, you have a pretty good understanding about friction. Alright, now let's go back to the question or the scenario I gave in the beginning of the video. So why all these situations are static friction? So consider this walking person. His foot or his shoes do not have real relative motion with respect to the ground because there is no real relative motion. There is only a potential motion. So her foot is pushing the floor push him as a reaction force, push him forward. So there's no real relative motion, only a potential motion. So it's static friction. And for a pure rolling ball, it's the same. The contact point between the ramp and the ball, there's no real relative motion. There's only a potential motion. So it's static friction. We're going to discuss more about this situation when we discuss rotation. And the same for the car. The tire is pushing the floor or the road. The road is pushing the car. And between the car and the road, there's no slipping. There's no gliding. In other words, there's no real relative motion. It only has a potential relative motion. So that's why under all three situations, everything is static friction. But why am I saying the friction force does not equals to mu s times Fn? Because we know this static friction force is smaller or equals to this maximum static friction force. So you only can know what's the real value if you have more information. The one last thing I want to emphasize, that is, if there is kinetic friction, there has to be real relative motion. In other words, the two contacting surfaces has to slide, skate, or glide. But if there are only potential relative motion, then you have static friction. That's all what I want to discuss today. Thank you guys. I will see you guys next time.